So remember, last class we were basically talking about how we are going to store data on a disk, right? So we had this picture of the disk that we were thinking of, where your disk has a bunch of platters or surfaces, and then each surface has a bunch of tracks or cylinders. Basically, the cylinder is just the same track on a bunch of platters, and then each track is divided up into sectors or blocks. And then the disk spins, and you have the read head that's actually reading, the specific sectors that you want. Right. So we talked about 4 different approaches for actually laying out our files on the disk. Right. So we started with contiguous allocation, which is where you're just picking some contiguous part of the disk, some number of blocks, one after another, to lay out your files. Then we talked about using a linked list approach, a linked file. Remember, and so the idea there was you have the first block of the file is what your inode structure points to, and then that first block has the first block of data, and then points to the second block, which points to the third block, so on and so forth. And then we talked about using an index structure where we had an index in the file descriptor of all of the blocks and where they were. And then we finally talked about a multi-level index structure. Remember, and the idea there was we could accommodate much larger files without having to cram the entire index into the file descriptor. So now that we've talked about how we're going to store data on the disk, now we need to consider how we're actually going to retrieve that data from the disk once it's already been stored there. So remember what we can say about how long it takes to actually do I/O from the disk. Right? So the 3 largest components are, we have a seek time, which is positioning that disk read-write head over the correct track, remember, while the disk is rotating. Then once we're positioned over the correct track, we have the rotational delay, which is where we're just waiting for the disk to rotate until the specific sector we want is under the read-write head. And then once we actually have the sector we want, then, of course, we actually do the transfer, where we're just either reading or writing from the disk. Right, so this is actually the only useful part of the disk I/O. Everything else, the seek time and the rotational delay are pure overhead. So essentially our objective in retrieving data from the disk is basically how can we do that while minimizing seek and rotational delay, because that's the pure overhead that takes so long because those are mechanical delays. So before we talk about any specific strategies, let's first just consider some actual typical parameters of a disk. To give you some idea of what these numbers are often like. Now these numbers are a couple of years old. 160 gigabytes is maybe not really the size of a disk you'd get today, but most of the numbers are still in the right ballpark. So your disk might have hundreds of gigabytes. Disks today might be 1 or 2 terabytes. You might have 8 or 16 platters on a disk, right? Those are the surfaces that are stacked one on top of another. You'll have order of several thousand tracks per surface, right? So that means that lots and lots of these really, really fine-grained tracks, these concentric circles crammed on each surface. And each track might be divided up into, maybe 100 or a few hundred sectors per track. We already said that, typically the sector, remember, which is the basic unit of I/O that the disk is mechanically capable of reading or writing, typically about 512 bytes. And your disk basically spins at a constant speed. Right, so a typical value for a desktop drive is maybe 7,200 RPMs, revolutions per minute. You could have a faster or a slower disk. And then, typical seek times to position the read head is going to be on the order of a few milliseconds, and similar for rotational latency. So on average, maybe you have to wait, half a rotation, which might be around 4 milliseconds. In terms of the actual transfer speed, right, you're looking at maybe 50 to 100 megabytes per second, so still pretty fast once you're actually reading. Now, disks are also going to have some amount of buffer that's basically going to let them store, a bunch of temporary data. We'll talk a little bit more about later about how we can actually use that buffer. And then, of course, your disk has some physical size. Right, so when you get a disk, you often get 3.5-inch hard drive is a typical size for a desktop drive. That basically refers to just the diameter of the actual platter. A laptop drive might be 2.5 inches. So in order to actually increase the capacity of our disks, right, typically what we're doing is we're basically taking these electronics and just miniaturizing everything, right? We make everything smaller, right? And so when we make everything smaller, that lets us do things like cram more tracks onto a given surface, right? If you have thinner surfaces, you can potentially pack more surfaces into a single hard drive. So maybe your previous hard drive might have had 8 platters. Maybe your next one has 16 because those are thinner. Or if we could also potentially increase the density of data by upping the number of sectors that we can store on a single track, right? So basically, these are all hardware constraints, and as everything gets smaller, we essentially naturally the capacity of our disks are constantly increasing. So, but for the moment, let's basically assume that we have some disk hardware. And we have chosen some file system layout. Either we're doing contiguous allocation or multi-level index or whatnot. And so now we need to decide how we're actually going to service our I/O requests in order to minimize seek latency and rotational delay. Right. So our objective is to minimize those two overheads. And a couple ways we could do that. So one is simply to make disks smaller. Right, so if we make our disk physically smaller, how's that actually going to help reduce our delays? Yeah. Right, so if you make your disk physically smaller, right, your read-write head is going to have to travel less distance to get to the track that you want, and your rotational delay is going to be less if your disk has less distance to spin. So we can of course also spin the disk faster. That will obviously decrease the rotational delay. Right, but those are, again, essentially just determined by the hardware. Right, so in the OS, we obviously can't affect that. So we instead need to consider things like how are we actually going to schedule our disk operations to minimize the amount of movement that read-write head has to do. And we can, of course, do other things that will have an impact on that, such as laying out data in an intelligent way. Right, because if all of your data is in one area that's sort of very compact on the disk, obviously, in order to read that data, your read-write head will have to do less movement than if your data is scattered all over the disk, and then you might have to move around a lot. Right, and so we also have a choice of where to put things on the disk. Now remember, assuming we're not using contiguous allocation for laying out our files, that's not a requirement to lay out data in a certain way on the disk. That would essentially just be an optimization. Right, because remember, one of the very nice things about the linked file approach or the index file approach was specifically the property that we don't have to lay everything out in one spot on the disk. But if we can do that, then that can be a nice optimization for reducing seek time. And we can also consider how to pick the size of blocks. And we think we talked about that a little bit last class, but right, if we have a larger block size, then we are essentially doing more I/O on each seek. So we're basically going to reduce the amount of time we actually spend seeking. But of course, if the block size is too large, then you start getting more internal fragmentation because you don't actually need all of that data for single files. And of course, again, this is all primarily a factor in physical magnetic hard drives, right? So when we're talking about solid-state drives where there's no moving parts, essentially most of these problems go away. We'll talk a little bit more about later in this class about some of the other issues you do run into when you're working with solid-state drives. But for the moment, we're talking about magnetic drives. So let's talk about how we can actually do the scheduling. Right, so the idea is that your OS is running a bunch of processes. You have a bunch of processes that are running, and each of them have some set of files open, and they're issuing reads and write requests. Right, so your disk is basically getting a constant stream of reads and writes coming from a whole bunch of different processes running, operating on a whole bunch of different files. So essentially, the idea in disk head scheduling is that we've got a bunch of requests to basically say, go read this particular sector of the disk. And typically, you may have many such outstanding requests at one time. Right, so the disk needs to make the choice of what request am I going to go service next? What sector will I go read next? And maybe others I'll defer until later. Right? And the choice of how we do that is going to have a major impact on what our access time looks like. Right? How much time the disk head spends moving. So we're going to talk about 4 different scheduling algorithms for scheduling I/O requests. One thing to note is that the algorithms we're going to look at are actually only trying to reduce seek time, right, which is the movement of the read-write head. They're not actually going to be addressing rotational delay at all, although I'll mention a few ways that we can also use of minimizing rotational delay. But for the most part, we're just going to be talking about minimizing the movement of the disk head and not about minimizing the time waiting for the disk to spin. So let's start with the first one. This will probably sound familiar. We start with the obvious thing to do, which is, again, first come, first serve. So let's say that we have the disk read-write head is positioned at some track, right? So let's say that we have 100 tracks of the disk laid out here, and obviously the read-write head is in some position. So let's say here the read-write head is positioned at track 30, and there's some outstanding I/O requests that we want the disk to service, right? So in this example, let's say we have 4 different requests going to tracks 65, 40, 18, and 78. Right, and so again, for the moment, we're just considering seek time, which means we're only caring basically about the track positions, not where not which sector of the track, because that's obviously what's going to affect the rotational delay. So for the moment, let's just say we're only concerned about seek time, and in first come first serve, right, we're just going to service requests in order of arrival. Right, so first thing we're going to do is we're starting at 30, and the first request we get is 65, right? So the read-write head is going to move to track 65 and service that request, right? Then we're going to get 40, so read-write head moves again to 40, then again to 18, and then finally to 78. So that's going to be the order of the seeks. We're essentially not doing any reordering here. And so then obviously the question here is how much time are we actually, or rather what's the distance of the seeks we're doing? Right, so the very first seek we're doing, if we're starting from 30 and we're going to track 65, so what's the distance we're traveling there? Right, so we're going 35 tracks. We're going from track 30 to 65, so that's a distance of 35. Then we're going from 65 to 40, so that's a distance of 25. Right, so on and so forth. We just add up all the distances, and in order to service these 4 requests using first come, first serve, we're traveling 142 tracks in order to do that. Now, this algorithm is obviously very, very simple, but it actually does work well in some cases. Right? So if your disk is not very heavily loaded, right, if you only have a few requests arriving, then this is probably fine. Right? Because if you only have 1 or 2 requests outstanding at any given time, then probably the most, it's a perfectly reasonable approach to just service the next thing you have and then move on. Right? It's only going to potentially be a problem when you have a lot of requests, and there you might be not, you might be incurring a lot more seek distance than if you were doing something more intelligent. Now, this approach is used in most solid-state disks. Right? Because remember, the idea there is we don't have this notion of a mechanical delay moving from one track to another. Right? In a solid-state disk, it's more like RAM, where you just access some block. It's like an array, and you can just jump to any block immediately. So if you can do that, then sort of the track positions don't really matter that much. Yes?
Well, my understanding is that on normal desktops, the QDEF length time is usually like 1 and 2.
The what?
The QDEF, which I'm understanding is the number of outstanding requests.
Yeah.
So this would work fine for desktop use, but not for server use.
That is probably, yeah. I mean, a server is typically handling a lot more I/O requests than a typical desktop machine. So yeah, that is probably true in most cases that, a server-type workload, which has a lot more going on at one time, is going to have more of a problem with this kind of simple approach than a typical desktop machine. But for something like a solid-state drive, this is basically okay at all times, since there's no added cost going from track 0 to track 100 versus track 0 to track 1. So let's consider a better approach if we do have a heavily loaded magnetic disk, which is going to be shortest seek time first, or SSTF. Right, so the idea here is we're always going to go to the next closest request. right? So this is sort of like what we were doing with shortest job first in CPU scheduling. At every time period, we're basically just going to pick the next best thing to do. Right, so let's say that we have the same 4 disk requests, and we're again, the disk head is starting at track 30. Right, so we have these 4 requests that are all wanting to be serviced. So what are we going to service first? 40. Right. Yeah, because essentially we need to consider what is the distance from the current head position of each of the outstanding requests. Right? So in this case, if we started at 30, the request at 40 is 10 tracks away, 18 is 12 tracks away, and these are obviously much more than that. Right? So the shortest seek time is going to be moving to track 40, given that we're currently at 30, so we do that. And then what are we going to go to next? Right, so now, again, same calculation here. Now we're starting at track 40. Right, so how far is it from track 40 to 18? It's 22. And obviously, 25 to track 65 and more to track 78. So the next thing we're going to do is we're going to go from track 40 to track 18. And now obviously the next closest request is 65, right? Obviously 65 is closer to 18 than 78. And then only one left, so we finally service the last one. Right, so this is basically a greedy algorithm, right, which is probably a term some of you have heard, where at each step we're basically picking the best choice one step into the future, the immediate best choice of what is the next closest request we can service. And right, that's quite easy because we're just essentially looking at the current positions that we want to go to and looking at the current position the head is at, and obviously it's just simple arithmetic to figure out which one you should go to next. So, is this going to be optimal? What do people think? Yeah.
Not always.
Right, not always. Right, so this is probably, it's a reasonable approach. Right, it's not going to ever do something obviously stupid. It's always going to the next closest track, but it's only optimal for the request that it's about to service, right? It's sort of one step in the future it's optimal, but in the aggregate, it may not be optimal at all. So actually, let's just sketch a simple example of how that could happen. All right, so let's say this is our disk, starting from track 0 and then going out to track 100, and let's say that the disk head is currently at track 50, and let's say that there's a request at track say 61, and then requests at say 40, 30, 20, and 10. Right, just as an example. So let's say we're at track 50 and we have 5 outstanding requests, 10, 20, 30, 40, and 61. Right, so what is shortest seek time first going to do here? What's it going to service first? Yeah. Right, so this is going to service 40 first. Then it's obviously going to service 30, then 20, then 10. And then you're going to have to go all the way back to 61. Right, and so if we tally up the distance of doing that, right, we have 10 here, so 20, 30, 40 plus 51. Right, so that's going to be 91. 91 tracks we're traveling to do this using shortest seek time first. But if we instead had gone here first, right, then this is going to be 11 to get here, and then 21, so 32 to get here, and then 42, 52, 62. Right, so we see here that clearly you could do much better than shortest seek time first if we instead went to this one. Right, because essentially, shortest seek time first is only looking one step. It's saying, it's going to be faster for me to get to 40 than it is to 61, which is true. But if you looked further into the future, you'd see that there's this one other request that you're going to be moving further and further away to, and sooner or later you're going to have to go back there. right? So that just gives us a sense that, this is a reasonable approach, but it's definitely not going to be optimal and can potentially do much worse than optimal. So not optimal, but still a reasonable approach. Any other problems people could potentially see with this approach? Yeah.
There's a little bit of overhead with a lot of requests, and you scan through all of them to figure out which one's closest.
That's true. So there's definitely going to be some bookkeeping associated with this. Certainly more bookkeeping than something like first come, first serve, where there's essentially no bookkeeping. You're just, keeping everything in the order it appears. Right here, there is going to be some bookkeeping. Now, one thing to keep in mind about bookkeeping that's different from things we've talked about like memory management is here we're talking about scheduling disk requests. But remember that the disk is so slow compared to something like memory that we actually can still reasonably do a lot more bookkeeping for scheduling I/O requests than we can for doing something like page replacement, right? Because we talked about how in page replacement, anytime we start dealing with data structures, we're essentially too inefficient to use because we're incurring that cost on every memory access. But every disk access is orders of magnitude slower already. So doing extra CPU work is actually a fairly small price to pay. So a little bit more overhead here, but still perfectly manageable. What's another problem, though? Think back to what we had with shortest job first. Yeah.
If you have a task that's really far away, you keep getting other tasks that are around the same area, you may never get to that one task where it really, really matters.
Right, exactly. You have potential starvation here, right? Because this is the same idea as shortest job first. Right, we talked about in shortest job first, if you have lots of short jobs arriving, and you have some long job that's been sitting around for a while, that long job might never get to run if you continuously have short jobs. Right, so the same idea is true here, right? If your, disk head is somewhere, down here in, 20 or something, and you keep getting read requests over in this part of the disk, then some request that's way over here may never actually get serviced if the disk is busy servicing everything over here. Right, so starvation is still a problem here. So, in this particular example, we essentially went over this already, but, the order of seeks, 14, 18, 65, 78. Of course, the, arithmetic is the same just to figure out the total distance of the seeks. And we already talked about, this is not optimal, because it's greedy. It minimizes the next step seek cost, but not the overall cost. And major potential problem here is that it's possible to get starvation. Now, so this is only optimizing for seek cost, because we're basically not taking into account where anything is on a specific track. But there's basically a variant of this called shortest access time first, or SATF. And there, basically, the idea is we want to optimize, both the seek cost and the rotational cost, right? Because basically, if you, lay out if you consider how your, disk is laid out, in a circle, and we have, some tracks of data, and we have, pieces of data at various parts of the disk that we want to get to, right? Essentially, what we want to do is minimize, the total distance between tracks that we're traveling, not just, one track to another, since there's a rotational delay at all. So we won't go into the details of that. But basically, I'm guessing many of you have heard of the traveling salesperson problem, right? That's a very well-known problem where it's basically what is the shortest path cost to traverse a whole bunch of points, right? And essentially, this is kind of an instantiation of the traveling salesperson problem where you have a bunch of points on the disk you want to get to, and you want to be able to do that, as efficiently as possible. Now, when you start doing that, you're complicating things, and there you really are introducing some additional complexity that is often, too much for you to reasonably want to deal with on every disk request. So something like this is actually, going to be typically more used than something that's trying to minimize, the complete access time, including both the seek and the rotational delay. So now let's consider a third algorithm. So this is called the scan algorithm. It's also sometimes called the elevator algorithm. So the basic idea here is think about how an elevator works, right? So the way an elevator works is it starts at some floor. Let's say it starts at the ground floor, and it goes up. And as it goes up, it picks everyone up who's going up And then once it gets to the top, only then does it actually reverse directions and starts picking up everyone who wants to go down. Right, so that's basically going to be the idea here. The read head is basically going to just be scanning back and forth across the surface of the disk, reading requests as it comes along them. Right, so let's say we have the same scenario as before. We're starting at track 30, and we have these 4 outstanding requests. Right, and we have to pick some initial direction for the head to be moving, but let's say the head is currently moving down. Right, so it's going to move down, deal with that request, and then start moving up, deal with all the requests that it hits there, and then reverse directions. And it's just going to continue scanning back and forth, right, and requests are going to be arriving while it does that, but it's essentially just going to keep the same movement regardless of what requests are arriving. Yes?
So to keep the requested blocks in a, does it keep them organized and lowest to highest? So the owner may just, it'll come all the way to 0, even if there's nothing at 0 in case something.
Yeah, so actually, there's basically a simple optimization of this, which is called look, the look algorithm. And basically, that's exactly what you're describing. One little optimization we can do with this is you don't have to actually go all the way to 0 or all the way to 100. Right? The optimization is basically just go to the lowest numbered request and then reverse direction, and then just go to the highest numbered request and then reverse direction. Right? So if we have these 4 requests, we don't need to scan all the way to 0 before reversing directions. We'll just scan to 18, which is the lowest numbered request. Then reverse direction and go up to 78. And then, assuming something else has, we have another request somewhere down here in the meantime, reverse direction again at 78. Right? Because if you go all the way to 0 in this case, we're basically wasting, 18 tracks going to 0 and then another 18 back when we could just reverse direction immediately. Right, so in practice, we are going to do that. So that's just called the look algorithm. Is basically scan where you're only going to the lowest request or the highest request. So the distances here are actually assuming we are doing that. Right, so that's assuming we are using the look algorithm. Right, so when we're starting at 30 and we want to go to 18, we're going to go 12. Well, that's obviously a distance of 12. But then when we want to go to 40, we're just going to immediately change directions and go to 40, so that's a distance of 22, rather than if we had gone all the way to 0 and then back up to 40, which would obviously be much higher. Now, in order to do this, right, we're basically just keeping some sorted list of requests, right, because the disk basically needs to know at any time what is the next request I'm going to get to. Right, so basically the way to do that is you're keeping a sorted list, and that tells you, that tells the disk, based on the direction it's moving, what the next request is that you're going to be able to service. So let's consider how is this better than shortest seat time first. Yes. Right. So, starvation is clearly not possible in this approach, right? Because with the exception of this little optimization that will sometimes make us reverse a little bit earlier. With that exception, right, the movement of the disk head is essentially not affected by the current requests that are coming in. Right, you're always just scanning back and forth. Right, so clearly you can never have starvation. Right, and you're only doing that, premature reversal when there is nothing more to service in that direction. So obviously, if there is a request there, at worst, you're basically going to scan through the disk once, and then your request will get serviced. Right, so nice benefit there. Can't have any starvation. How might this actually be worse than shortest seat time, though? How might this not do as good as shortest seat time first? Yeah.
Maybe if a disk request pops up after it's already moved past a certain point, right after, so it could be very, very close, but it has to swing all the way back around before it.
Right. Exactly. The point here is that you might actually have higher seat times than in shorter seat time first. Right? Because as the read head is moving back and forth, maybe you're moving from track 0 to track 100, and maybe you just passed track 50 when a new request arrives for track 49. right? So shortest seek time first then would basically jump to 49 because that's really, really close. But in the elevator approach, you're basically just going to keep on going. You know, even if you're traveling to a request at track, 300, you're still going to go all the way there. Yeah.
So my question for that would be, if you're, so say you're at 40 and you're working your way to 65, and you just pass 50, and then the request for 49 comes up, shortest seek time first, won't that already be going to 65 and then 40?
Yeah, that's actually a good point. Yeah, so in general, you're not going to stop servicing a request that you're already moving to in order to service something else. Now, actually, I'm going to mention this later, but I should mention this now. So right now, we're basically assuming that when you move from a track to another track, that the time it takes to actually do that is basically just a linear function of the number of tracks. Right, so we're sort of assuming that to move from track 10 to track 20 takes twice as long as moving from track 10 to track 15, right? Because you're traversing 10 tracks instead of 5, so it takes twice as long. But in reality, a disk doesn't actually work like that. Remember, because this is all mechanical process of the read head moving from one track to another. And so it doesn't move, the read head doesn't move at a constant speed between tracks. It's actually more like a car, right? Because when you are driving a car, you basically are accelerating up to a certain speed and then moving, steadily at that top speed and then decelerating, once you're very close, right? So the disk head is basically going to do the same thing. So if you're moving from track 0 all the way to track 100, you're basically going to accelerate and cover that distance relatively fast, versus if you're moving, just track 0 to track 10, say, that's going to take much longer than 1/10 the time, right? Because the read head is going to accelerate and then decelerate. So if you're only moving one track or a few tracks, you're essentially just nudging the read head a little bit. You can't just immediately take off at top speed, right? And this is, again, essentially a limitation of the mechanics of how the disk is actually working, right? Because remember, we're talking about thousands of tracks on a single, couple of inch surface, right? So those tracks are, order of 1 or 2 millimeters apart, right? So when you have tracks that are that close and you have a mechanical head moving across them, in order to get high precision to a specific track, when you're moving a short distance, you're not going to be able to do that really quickly. So that's actually a nice segue into the fourth approach, which is basically going to be a modification of scan. Oh, sorry. Yeah, that's the animation again. Okay, so the modification is basically called C-scan, the circular scan algorithm. And the idea here is that rather than just doing an elevator going 0 to 100 to 0 to 100, we're basically going to think of it as sort of wrapping around. So we're going to service requests from 0 to 100, and then we're going to start servicing requests again, starting from 0. Now, the disk, of course, has to actually get from 100 back to 0, so it's essentially going to reset. Right, so if we have this same example again, we're going to service everything there, and then we're going to reset back to 100, and then start scanning this way again. Right, so each time, we're not just going to reverse and go the other direction, we're just going to go from one end of the disk to the other and then start scanning in the same direction again. So the reason this is a nice segue is, why might we actually want to do this over just servicing all the requests on the way as we go from one end of the disk to the other? Yeah? Yeah, so that's one very good point, is that, right, so after you've completed a scan, let's say we're using elevator again, and we've scanned from 0 to 100. So once we're sitting at 100, where are most of the outstanding requests likely to be? Right, if we assume that a request is going to arrive sort of uniformly at random, right, if we assume that a request is as likely to arrive at any part of the disk, and we've just scanned through from 0 to 100 servicing requests, where are most of our outstanding requests expected to be? Yeah. Right, closer to 0. Right, because as we're traveling this way, we're scanning requests. So once we get to 100, you know, a request that was at 90, we just serviced that just a moment ago. Right, so it's much less likely that there's a request at 90 because we just recently serviced that versus a request at, you know, 10 or 20, which it's been much longer since we serviced those. Right, so what we tend to expect is that once we've completed the scan, most of the requests are going to be clustered somewhere on the other end of the disk. So that's one reason to do this. But essentially my original question was, well, if we're having to move the entire head from, you know, track 0 all the way to track 100 to reset anyways, why don't we just service all the requests along the way? Right, because that's the difference between the circular scan and the elevator, is that once we're resetting from track 0 to track 100, as in we're doing here, we're not going to service those requests even though we're passing them over. So my question was, and this is related to what we were just talking about, the speed of the disk head, you know, why might we not just service everything as we go over them? Yeah.
Would it be faster to do that just to travel, because it essentially can use top speed, I guess?
Right.
By jumping to 100 and then working instead of that.
Right, so basically the idea here is that when we're scanning all the way from one end of the disk to the other, we're obviously getting the disk, you know, up to the disk head up to top speed. So it would take longer if we had to sort of slow down along the way to hit a couple of intermediate steps. And then also, of course, when we're actually servicing requests, we're also incurring that rotational delay. So it is going to delay other requests that we're getting in the future. Do you have another question?
Yeah, so isn't it going to have to stop anyways when it hits the track from, or track it is trying to read data from, such that rotational delay, or it rotates in the position too? Would that cause a deceleration in your read, essentially?
So remember, so the acceleration-deceleration issue is just an issue with the read-write head, right? Because remember, the disk itself, the platter is spinning at a constant rate. So the read-write head is moving between tracks,
Right.
and that's where it's going to have some acceleration and deceleration. While it's doing that, the disk is itself, the surface is just rotating at a constant speed.
What I was saying, I guess, wouldn't the disk head have to stop for a period of time to do a read?
Yes, yes. So if you're servicing requests along the way, then you are basically, in addition to the issue of having to decelerate to reach that track, you are then still having to wait for the rotational delay. So yes, that's true. Yeah. Other question? Well, so remember that we're talking about tracks here, right? So the tracks are these, you know, concentric circles of the disk, right? And so the read head is, you know, over one of these circles, and basically can move between, you know, track to track to track, essentially. So, you know, we're just basically scanning, you know, track 0. This might be track 0, and then out here somewhere we have, you know, track 100. So we're essentially just moving from the inside of the disk to the outside of the disk, or vice versa. Does that answer your question? So, what is a? So I guess we already sort of addressed that. You know, why might we want this instead of scan? Is essentially that we're going to have, you know, more uniform request times, right? Because if we're using the elevator approach, requests at either the beginning or the end of the disk are on average going to have, you know, better performance than requests in the middle of the disk, right? Because once you get to the end and you change direction and scan back the other way, you're basically servicing, you know, requests at the bottom or the top of the disk twice in short succession. You know, versus the circular scan algorithm is not basically going to favor, you know, tracks at the beginning or end of the disk versus tracks in the middle, right? Because you're just scanning over it, you know, essentially in a circle rather than, you know, back and forth. Come on. Okay. Oh, so one other thing I wanted to mention about these approaches. So those are basically the four basic approaches. Now, one thing is that most of these approaches are typically implemented in the disk driver itself, right? So basically, or sorry, rather the disk controller itself, as opposed to the disk driver, right? So your disk basically has some little piece of built-in software that's running sort of on the disk itself, on the disk hardware, that's actually typically running one of these approaches. So for example, like the elevator approach is actually used in a lot of sort of off-the-shelf disks. Now, it's nice to basically offload that to the disk itself, but if we wanted to do sort of more complicated approaches, such as the approach where we're trying to minimize complete access time, and we're having to do potentially more computation, there we might actually want to move the logic of how to schedule the disk requests into the disk driver, right? Because the disk driver is basically a piece of the kernel, as opposed to the disk controller, which is basically sitting on the hardware itself. But in general, most of the time, these approaches are running within the disk controller, so we tend to prefer more reasonably computable approaches such as these. So one other thing about C-scan is that we can essentially do the same exact optimization as in look, where we are saying this is essentially the C-look optimization, where we again can just go to the lowest request and then reverse direction to the highest, and so on and so forth. Right. So same exact optimization there. So this calculation here with the distance of the seeks. Right, so again, here we're going to go first to 18, then scan all the way back and start from the top and come back to 0. And the distance of seeks here is assuming that we are using the look optimization, where we're only going to the lowest numbered request before scanning back up to the top, which in this case is 78 rather than 100. Okay, and then we already talked about more uniform wait times. Okay. So that's pretty much it for disk head scheduling. Right. So idea there is we're just trying to reduce the total seek time, and potentially, depending on the approach, also possibly the total access time, including the seek and the rotational delay. But now let's consider a few other possible optimizations. So here's one possible problem that it's good to keep in mind is, right, so we were talking about contiguous file allocation, right, which is where you're basically just laying out the blocks of a file one after another on the disk. And we said that, if you want to do sequential access of that file, if you want to read the entire file, right, then that's basically the best possible approach, right, because the disk is just going from one block to another, and that's always the next block you want. But remember that the disk is constantly spinning, right, regardless of things that we're requesting. Right, and so essentially there's going to be some latency for the OS to actually go ahead and request the next block that we want. Right, so if we're going from block 1 to block 2, the OS is going to have to process block 1 and then issue a request saying give me block 2, but the disk is still spinning. Right, so you could have the case where you essentially request the next block of data in the OS, but the disk has already physically spun past that block of data that you want. And so if that happens, then what are you essentially need to wait for? What do you need to do? If you essentially just spin past the piece of data you want. Yeah. Right, then you essentially need to wait a complete rotation for the disk to get back around. Right, so that's a possible issue if essentially the disk is spinning too fast for whatever the OS is able to process. Then contiguous allocation may actually not be really good, even if we're just trying to do sequential access. So one idea that we can do to actually deal with this is called interleaving. So the idea here is that rather than actually laying out the blocks of the file in an actually contiguous fashion, we can basically allocate them with gaps. Maybe we allocate every 3 blocks, we stick a block for the same file. Right, and so the point there is that by adding little gaps, we can actually accommodate, the latency of the disk without actually going past it, right? Because then we basically are giving the disk a little bit of time to spin until the OS issues the request for the next block. And then hopefully once we do have the request for the next block that's been sent to the disk, we haven't actually spun past the block because we had a little bit of a buffer there. Right, so basic idea makes sense, right? So you could use, every second or every third block rather than, one block after another. So, the file will be block 1, and then the next block of the file will be in block 3, next block of the file will be in block 5, so on and so forth. Right, so that's the idea of interleaving. So that's sort of one approach that allows for some I/O latency. What might be another approach? Right, if we want to essentially deal with the problem that oftentimes we want to read blocks sort of one after another if we're reading a single file, for example, a large file. What might we be able to do instead of basically changing the layout of the disk? Any ideas? Yeah. Increase the buffer size. Yeah, so what can we potentially do with the buffer? Right, so basically your disk has some buffer space that you can basically just use. It's basically used as a cache, right? And so if you've got this cache space and you are spinning over these consecutive blocks of a disk, basically the idea is that we can read in some of those blocks even if we haven't actually gotten the request for them yet, right? Because if you're reading a sequential file, chances are very good that if once you've read block 1, the next thing you're going to want is block 2. Right, so your disk can basically read blocks that you haven't actually requested yet and store them in the buffer cache. So this is called doing read ahead. Right, so the idea is that ahead of actually receiving the requests, we can actually read in some extra blocks and place them in that buffer. Right, because that buffer on the disk is typically maybe a few tens of megabytes. So certainly large enough that it can store quite a bit of information. Right, so the disk is spinning and all of that data is passing under the read head, and we're basically just going to typically read the entire track. Right, because we can easily do that and store that in the buffer. So even if I only requested maybe one particular sector of the track, we're just going to start there, right? We're going to seek to there, and then while the disk is spinning, right, it's basically free to read all of that extra data. Right, because we're not incurring any extra seek time because we're still on the correct track, and chances are good that the application is soon going to request those pieces of data as well. So we're just going to read them all and store them on the disk. Right, and of course, if we guess wrong, then essentially it's harmless. We're essentially just we used a little bit of cache space, but that's no big deal. We can basically just discard them, and no harm done. Right, so goal here is basically reducing the number of seeks because you just did the one seek, read in all of the data, stored it in the buffer, and then once a subsequent request arrives, assuming you have that data just sitting in the buffer, your disk doesn't need to do anything at all. Right, you've already got all that. So this is of course this idea is of course basically betting on the fact that you have some contiguous allocation on the disk. Right, because we talked about that if your file is not laid out contiguously, you could potentially have blocks all over the place on different tracks. And of course, if that's the case, then prefetching, read ahead is not going to do anything for you. But again, in most cases, we will often have contiguously allocated data, even if we're not using explicit contiguous allocation. Right, this is again what we talked about. We don't need to have contiguous allocation, assuming we're using something like a multi-level index, but we still can do that as an optimization, and that will let us do things like read ahead, because some of our data will still be laid out contiguously. So this I've described as actually basically disk level read ahead, right, where the disk is actually spinning and covering a certain track. And while it's rotating across that track, it will just read in all of that data because it's essentially free. But you can also have basically what we call file system level prefetching. Right? And so the idea here is that if your OS is reading a file, right, and you are reading a file and you see that I requested blocks 1 of the file and then I requested block 2 and block 3, pretty good chance that you're about to request block 4 and block 5 and so on and so forth. Remember, and those are not necessarily on the same track, right? Because depending on how the file system is laying things out on the disk, those blocks of the file may be in completely different parts of the disk. But we can still essentially do file system level prefetching and request those blocks of the file in advance, right? So that is potentially incurring seeks, right? Because when we're requesting some other block of the file, that may be on some other track and causes the disk to seek to that track. But same basic idea, if we think there's a good chance we're about to request those blocks, let's just do the seeks now, pay that price now, and then when we actually get the request in the future, we won't have to wait for the seek then. Right, makes sense the difference between the disk level and the file system level read ahead? Right, same basic idea, but one of them is going on sort of at the level of hardware, and the other one is going on actually within the file system where we're requesting other blocks to prefetch. So now let's also consider, right, this is kind of similar to the idea we mentioned a little bit when we were talking about memory management of potentially, prefetching virtual pages. But we basically said that we only talked about that a little bit, and we essentially said that was, fairly difficult to do because which pages you're about to use are potentially, difficult to predict. So any ideas why, sort of disk read ahead might be better than fetching pages of memory? Yeah.
Pages are like factual code, rather as if you're going through a file, you're probably going to read the next line of the file, but you might not call the next page of that code.
Right, exactly. Basically, pages of memory are sort of pulled in from just about everywhere. Right, so if you are running your program and it's calling, a program is typically, say calling code from bunches of shared libraries that are all over the place. Right, and so your code is going through a lot of conditional branches and maybe jumping all over the place. And so you may be pulling pages of memory from all over the place versus with disk, you're typically not going to be accessing 1,000 different disks in sort of a random fashion. Right? The order of disk accesses is typically much more predictable than the order of page accesses. And you're typically going to have more locality in what you're accessing on a disk than where you're actually fetching memory from. So it's for that reason that prefetching pages is sort of rarely used, but prefetching disk is actually very frequently used. Okay, so now let's talk a little bit about solid-state disks. Right, so we've already talked a little bit about this, but basic major difference is that solid-state disks have no moving parts. Right, so the underlying technology is basically closer to RAM. It's flash memory, right? And flash memory is used in a lot of other different types of devices that are very common. Things like a USB thumb drive or an SD card. Right, these are all essentially flash storage, and that's basically what a solid-state disk is. It's a much larger amount of flash memory combined with some controller that's going to do some more intelligent things with that, and we'll talk about what some of those are. But it's doing random access without having any of the disk movement head, right? You can basically envision your flash storage just as you do main memory, right? You have blocks, 0 to 1,000 or whatnot, and you can just directly request block 3 or block 200, and you can just immediately go and get that. Right, so because you can essentially do that, your reads are very, very fast on solid-state drives, because you don't have to wait for these seek or rotational delays. You can just jump to whatever the piece of data you want and read it immediately. So reads are very, very fast. Now, writes are actually somewhat slower than reads. Now, this is kind of different from a magnetic disk, because normally when we're talking about a magnetic disk, you get to the part of the disk that you want, and then you either read or write the sector, but it's sort of the same, essentially the same overhead. But with a solid-state disk, you essentially can't directly overwrite a piece of data on a solid-state disk. Right? Instead, you basically have to first go and either reset, or sometimes the terms are used basically reset or erase, and essentially mean the same thing. But basically, a cell of your solid-state disk needs to be erased before you can actually write to it again. That's basically just a property of how the technology works. You can't just overwrite the existing data. And so that means that in order to actually overwrite something, you're basically doing two operations. First, you're resetting it, and then you're actually writing it with the new data that you want. So in order to basically deal with that, when you are, say, overwriting a file, right? So when you have a file open and you're changing it, typically on a hard drive, what you're just going to consider is that, well, you go to where the file is stored on the disk and you overwrite it, right? That's sort of what we think of when we say overwrite. But on a solid-state drive, you're typically not going to do that. Instead, what you're basically going to do is go to some piece of the disk that is not currently used and write the new copy of the file to there, and then you'll basically just update your inode to point to the new copy. Right, so if you just have, a disk here, this is your solid-state disk, and you have, your file is stored here, this is, after file, and you want to overwrite that, rather than, storing it over here, we're just going to pick some unused part of the disk, call that F prime, and then, you have this, this inode structure that's actually saying where the file is located on the disk, that was previously pointing to the file. Now you're basically just going to change the inode to point there, get rid of that. So the file is still going to be stored there, but you're now not using that. And then what we're essentially going to do is, in the background, we're basically going to run garbage collection. Right, so I'm sure you all essentially know what garbage collection is, where we have these used but not needed pieces of the solid-state disk that in the background we're just going to erase them. Right, because in order to use this again, first we need to do an erase to it. So now our file system is basically needing to track some extra information, because remember the regular the magnetic disk, all we're basically tracking is where our files are and what the free blocks of the disk are. Right, we had the free block list. Now we also have the addition of essentially the list of blocks that are used but awaiting a reset. Right, and so that's in the background, we're just going to reset those so that when we ultimately have use for it, it will already be reset and we can just write to it directly. Now, another important property of flash drives is that you can actually only write to a certain block of the disk so many times before it actually wears out. So, for example, on a typical solid-state drive, maybe you can only write to each block of it maybe a few thousand times, for example. And once you've written to the same block that many times, it essentially can't be overwritten anymore. Right? This is, again, just basically a property of how flash storage works. So, given that's the case, what do we probably want to do with how we're actually choosing pieces of the disk to use? Right, so if I have a file and I am writing somewhere, I have a choice of, whatever open parts of the disk that I want to do. But what I don't want to do is, say, overwrite the same location in the disk over and over again. Right, because then you're essentially going to wear out part of your disk quicker. Yeah. Right. Right, so this is the idea of wear leveling, which is basically that we're also going to need to track how often we've actually, or how frequently we've basically overwritten each block of the drive. And we basically want to keep that balanced, right? Because you don't want to just constantly overwrite a few blocks of your disk, wear them out really quickly, and then all the other blocks have sort of very rarely been used, right? Because then you're basically just, destroying part of your disk for no reason. So we're also going to basically try to balance where all of our writes are going. So that's, again, sort of another added complexity that, the disk controller is basically having to deal with a solid-state drive in order to preserve the life of your disk. So this actually is not so much a problem in a solid-state drive you might buy now. Solid-state drives have been around for, a couple of years now, have gotten much more common. But, probably maybe 5 years ago, sort of the first generation of, consumer solid-state drives you could get, this was actually a very real problem, where if you were running really I/O-intensive workloads on your solid-state drive, you might actually wear the drive out in maybe a year, right? Because essentially you're just running through all of the write cycles, and if you're not wear leveling correctly and you only have so many cycles, then you can essentially kill your drive by using it too much, which is really not a consideration we have in a traditional hard drive. So, basically compared to hard drives, solid-state drives are basically, faster, much, much faster. That's obviously the big upside. Also typically physically smaller. And of course, the major downside is that solid-state drives are much more expensive than a magnetic hard drive, right? Because in your laptops, you probably have what a solid-state drive that's maybe 128 or 256 gigabytes of storage, versus a magnetic hard drive of the same price, you could probably get 10 times as much storage, right? So that's the major downside, is that they're still, and obviously prices are falling all the time, but still much more expensive, per storage than a magnetic drive. One other thing I actually want to mention about the overwriting issue is that some of you may have noticed, if you've ever gone and sort of ordered a solid-state drive or looked at solid-state drives, is that oftentimes the size of the drive looks kind of weird, right? So when you go and you buy a hard drive, oftentimes it's a terabyte or 2 terabytes or 512 gigabytes or whatnot, sort of typical sizes. But oftentimes with a flash drive, with a solid-state drive, you'll see sizes like 120 gigabytes or 240 gigabytes, right? And obviously that hopefully seems a little bit weird, because what you would expect is 128 gigabytes or 256 gigabytes, right? Sort of the typical powers of 2. So essentially what's actually going on there is your drive is basically shipped with a little bit of extra flash storage that is basically not available for you to use. So this is basically your drive is basically over-provisioned with some extra storage that it can use to basically maintain the lifespan of the drive. Right, so if you buy a 120 gigabyte solid-state drive, typically you are actually getting 128 gigabytes, but that last 8 gigabytes is basically reserved for the disk controller to use in wear leveling, basically. Right, so that's, again, essentially you're losing a little bit of storage due to this fact of the controller needing to preserve the life of the drive. Okay, so RAM obviously is what we mean by primary storage. When we call primary storage is main memory, and the disk is usually what we call secondary storage. Now, we can also basically consider a third level in the storage hierarchy of what we call tertiary storage. And this is where we're basically, obviously the main difference between a disk and memory is that a disk is much cheaper, much larger, and much slower. Right? And we can actually basically continue that, go to tertiary storage, which is going to be cheaper, larger, and slower than a disk. Right? And typically what we use tertiary storage for is basically just things like archiving and backups, where oftentimes we're not actually basically needing to do any random access. It's just going to be sequential access for the purpose of doing archiving. So now these are these types of things are largely not used as much as they used to be because disks have gotten so cheap and so large. But things like tape drives are sort of the classic example, where my guess is that none of you have ever actually seen a tape drive, but basically, it's like you envision a VCR type. It's basically actually just tape that is storing data, and a tape is basically very inexpensive and holds a lot of data. But in general, you basically can't do direct access on a tape, right? Because if you again sort of envision a VCR when you're playing a tape, in order to get to some other part of the tape, you basically have to either rewind or fast forward to get to that point. You can't just jump to any part of the tape, right? So basically, you can only do sequential access rather than random access, right? So obviously, this is not suitable for running your OS when you're not able to do any kind of efficient random access. Doing random access might be 2 orders of magnitude slower than using a regular conventional hard drive. But if all you're doing is archiving a ton of data, you're basically just writing out a bunch of sequential data to the tape. That's fine. The speed of doing that will be similar to what you get with a typical hard drive. And if you're restoring from an archive, that's going to be similar. You're basically just reading through your tape sequentially, and that again is going to be perfectly fine even if you don't have random access. Okay, so last thing I want to talk a little bit about is RAID. So let's consider a large server environment. Now typically when you have a large server, you actually have a lot of disks, right? So when we're talking about your own laptop or your own desktop computer, oftentimes you might only have one hard drive. That's your machine's hard drive. But when you have something like a server that's managing a lot of data, typically you have a lot of hard drives. And so let's consider the problem of what happens if a hard drive dies, right? Because we all know that hard drives can die. Actually, just show of hands here. Who's lost a hard drive before? Yeah, most of you. Yeah. How many of you kept backups before versus after the hard drive failure? Yeah. So if you, let's say that your hard drive, on average, typical figure, maybe a hard drive is expected to last 100,000 hours. That's what we call the mean time to failure. Basically, how long you expect the hard drive to run before it dies, for whatever reason. Actually, just as an aside, often one of the ways that a magnetic hard drive dies is, again, you have that magnetic read-write head. That's basically a tiny, tiny bit above the disk surface. But essentially what can happen is if your hard drive essentially has a very slight mechanical malfunction, your read head can basically crash into the surface of your drive, and that's often what it is. If you have, I don't know if any of you, when your drives have failed, you often get what's called the click of death, which is basically where your drive is clicking and you can't read anything from it, and oftentimes that's a symptom of the fact that your disk head has essentially just crashed into your drive and ruined all your data. So in any case, let's say that a typical hard drive might last 100,000 hours, which is about roughly 10 years. But now let's say that you have a big server environment where you have 100 disks rather than one. So now on average, what's the mean time to failure? How long do you expect to have before one of your disks fails? Yeah. Right, basically, 100 times shorter. Right, so if you have 100 disks, then your mean time to failure is only about 40 days. Right, so you expect that in the span of roughly a month, one of your drives is going to die. Right, and so basically then the issue of providing safety for your data when drives are expected to die is an important issue. So this is basically the idea of disk arrays. Right, so what we've been talking about so far is, you have one disk and the one physical disk that you're talking to. It's a single logical disk. But basically the idea of a disk array is we're going to have multiple disks. Maybe we have 4 hard drives. And we're basically going to consider all these drives as a single logical unit. Right, so when our OS is reading or writing to our hard drive, it considers it a single logical drive, but it's actually backed by, say, 4 different physical drives. And so there's a few different ways that we can use this to help us. Right, so one way we can use this is what we call striping. Right, so the idea in striping is basically where you're going to take your file, and if I have the big file that I want to write, I'm basically going to stripe it, distribute it across multiple disks. Right, so if my file has 4 different blocks of data, then I'll store one block on this drive, I'll store another block on this drive, so on and so forth. I'll basically stripe my blocks of my file across the disks. And this is basically what we call RAID 0, where if each of these drives, let's say, are 1 terabyte, and we have a RAID array of 4 1 terabyte drives, then if we're using RAID 0, we're basically just striping data across all of these drives, and this array is going to give us then 4 terabytes of data, right? Because we still have the storage in each individual drive. And so RAID 0 is basically just where we have our blocks of data and we're distributing them across the drive. And the main thing we get from that is much better performance, right? Because now essentially when I'm requesting files, I have 4 different drives, 4 different hard disks that can be reading data at the same time. Right, so we're essentially getting some parallelism here, and we're able to service a lot more reads faster and potentially read a single file faster since it's distributed over an entire disk. So that helps with performance, but this doesn't actually help at all with reliability, because if one of these drives dies, let's say that this disk, the 3rd disk, dies, what's happened to our file if it's distributed across all the disks? Right, because we essentially had just lost part of the file. Essentially, the whole file is ruined. Right, so that's actually even potentially worse from a reliability standpoint, because even though we only lost one of our disks, we might lose a ton of files, basically anything that was distributed and included some data on that disk. Right, so another type of RAID is what we call RAID 1, which is where we're going to use what we call mirroring. So the idea here is that we're basically just going to take all of our data, pieces of blocks of data, and mirror them to another physical hard drive. Right, so now, if, this is, D1, this is the first physical disk, D2, D3, and D4. Now what we're going to do is we're just going to store our data on D1 and D2, and D3 is just going to be used as a complete copy of D1, and D4 will just be used as a complete copy of D2. Right, so benefit of here, this is what we call mirroring. Benefit of this is that if, D2 dies, what can we do? So have we lost data if D2 dies? Yeah. Well, you still have D1, but...
So you said D2 dies?
Yeah.
You still have, you don't lose anything.
Right, because you still have that, all that data is mirrored on the fourth hard drive. So remember, this is still all operating as one logical drive. So basically what the RAID controller does, so actually I guess I didn't actually define, but RAID is basically just means a redundant array of independent disks is what that stands for. But basically if D2 dies, the disk controller is directing requests to both D2 and D4. So we can now just start using D4, and we essentially have no downtime, no lost data. And so then, someone later can come in and basically swap out D2, which has failed, with a new hard drive. And then, D4 will be mirrored back onto D2, and you now have, full redundancy again. Right, so essentially using this scheme, you can handle drive failures without losing data. Now, of course, the main downside of this is, what is the main downside of doing this? Yeah. Right. Essentially, you have only half the capacity, right? Because if each of these, again, are, say, 1 terabyte disks, if we're mirroring, how much effective capacity do we have in this RAID array? 2 terabytes, right? Because we can store data in here and here, but D3, these 2 physical disks are being taken up by mirroring, right? So this is the idea of RAID 1, where we're just mirroring everything. And there's basically a bunch of different levels of RAID. There's 6 different levels. They're covered in the book, but we don't need to go into too much detail on them. But essentially, the more advanced types of RAID, which I don't have time to get into detail, but like RAID 5 is the one that's most typically used. Basically, the idea is that rather than keeping a copy of everything, you're just going to keep what we call parity bits. And so the idea of parity bits is basically that you're going to keep one extra drive. So, in this example, we maybe use D1, D2, and D3 to store our actual data. And then D4, this one drive, is going to be used for parity information. And essentially, the idea of parity information is that we're going to store bits that are going to allow us to reconstruct one of the other drives that failed. Right, so let's just give a really simple example of the idea here. Right, so let's say that our drives are just storing 1 bit of data. Absolutely most simple case. So let's say that on D1 we have a 1. On, say our drive 1 has a 1, we have a 0 on D2, and we have a 1 on D3. So what we're going to store for the parity bit is basically a 1 if the sum of these bits is even, and a 0 if the sum of these bits is odd. Right, so D4, this is parity. We're just going to store a 1 there. And so now, and then this is going to be repeated for, potentially every single other bit. D1, D2, and D3 have some bits, and then the parity is going to store either, 0 or 1. And now, your basic idea here is, let's say that D3 dies. But using these parity bits, we can actually reconstruct what D3 was supposed to have, right, using these parity bits. Right, because we just constructed them so that, in this case, the sum is, actually this is, right, we just essentially constructed this so that the sum of all the bits is odd here. Right, so we have 1 plus 1 is even, so the parity bit's going to be a 1. And 0 plus 0 plus 1 is odd, so the parity bit's going to be a 0. Yeah?
What's one of the limitations on the number of disks for wave files? Like, say, if you're using on the number of disks?
No. So basically we can have any number of disks and the one parity drive. And that one parity drive is basically going to allow us to reconstruct any single drive that died. So any one of our drives can die, and using that parity bit, we can reconstruct the one drive that died. Of course, if 2 drives die, then we're essentially out of luck. But of course, the idea is that as soon as a drive dies, in short order, you actually go in and replace it. Other types of RAID that do things that are more sophisticated. So RAID 5 is actually not keeping all the parity information on one disk. It's basically distributing it across all the disks. But we don't need to go into that. So I think let's stop there.